expert in inflation and scattering amplitudes during inflation, and maybe cosmic accelerator and things related to very early universe. And as you see, all these different topics in these lectures, they have some unavoidable overlap. So it's really good that you're going to see things that are similar in the beginning from different lectures and from different perspectives. So it's a real pleasure to have Gonzalo here with us. And this is the first lecture on primordial cosmology. Thank you, Gonzalo.
Yeah, thank you very much, Rogerio. Can you hear me well? Yes? Okay, great. Well, first of all, I want to thank the organizers for this invitation. It's a real pleasure and an honor to be here with you. So please feel free to interrupt me at any time. So if you have any questions, don't hold them back, okay? As a primordial cosmologist, I will be teaching you all the time. So I will not tell you the whole story. So if you don't make questions, means that you either did not understand me or you knew already what I'm talking about, okay? So I expect questions from time to time. So let me, today, I mean, primordial cosmology is quite a big topic. It continues to develop quite a lot even today. Even though we are a bit stagnated with data. So the theory is proliferating quite fast. It's inflating, if you want. However, we're waiting for data to be able to say more about the cosmos at the first stage that we believe it happened. So then the modern paradigm to understand the origin of the universe is cosmic inflation. So when I say primordial cosmology, cosmology means the study of the origin of the universe, in a sense. But it has become basically equivalent to cosmic inflation. So inflation has basically pushed away other contenders to explain the origin of the universe. And now it's basically the framework to explain why the universe looks as it seems to be looking right now. Yeah. So I'm really thankful to come after Roman because he introduced already quite a lot of important things that I will be profiting from. So he mentioned concepts such as stochastic fields, Gaussianity. He introduced also the concept of contrast and so on and so forth. And I suspect he will continue to do so tomorrow, and I will be borrowing a lot of ideas from him. So I think that this way of organizing the lectures, at least for me, has been quite useful. I will try to get to the point today where I actually introduce the concept of Gaussian fields, because they actually do emerge within the context of quantum field theory. Okay, so for today, my plan is to give, first of all, an overview of what do I mean by inflation. So I cannot be too precise about it, but I just want to give you an idea. What are we talking about when we say inflation, okay? And after that, I want to jump into more fundamental things, such as quantum field theory. I'm assuming that most of you have a good background on general relativity. Unfortunately, that's an assumption I have to work with. But I'm not assuming that all of you have a good grasp on quantum field theory. In fact, I want to start by making a survey here. How many of you have taken a standard course on quantum field theory? Okay, that's fantastic. It's almost everybody, but still there's some people that didn't raise the hand. So my purpose here is to offer a review of quantum field theory, but also I want to emphasize things that will be important for inflation, okay? So please interrupt me at any point if you have questions about quantum field theory. I will start with quantum field theory in Minkowski spacetime, which is what you probably studied in this standard course of quantum field theory that you admitted you took. And then I will jump into something less standard that you probably didn't see in those courses, which is quantum field theory in time-dependent backgrounds. Essentially, it's the same theory. This is not, in terms of the tools, we're talking about the same thing, but I just want to offer some language that we will later use for inflation. Okay, so that's a plan for today. I'm not very sure I will be able to go through all of it. It doesn't matter. If not, we just continue tomorrow. Okay, great. So let me start with a picture. So often cosmologists draw time in some direction. Let's do it vertically. And then I will draw space, or more than space, distances in this horizontal axis. Okay, so this is a plot of space-time, and I will try to condense the history of the universe in this plot. So we are at some point, let me draw us in the origin, sort of spatial origin, right? So we are at x equals 0 or r equals 0, whatever coordinates you're working with, and we're watching the universe. Okay, so what we watch are galaxies. Okay, so I'm very bad at drawing galaxies, but something like this. Okay, so here you have galaxies. Okay, I'm already cheating you, by the way, because you know that we, in a plot like this, we don't really observe galaxies at a fixed time. We observe into the past. Okay, I will take this license. I think we all understand that. Okay, so I'm just imagining that in this plot, we are able to reconstruct galaxies in this fixed time spatial axis. Okay? Okay, so the universe is expanding, so that means that galaxies were closer and closer into the past. Okay, so that means I will draw the trajectories of galaxies in this plot, and you know that this is the Hubble's observation. Galaxies basically have a history into the past. Galaxies did not exist all the time into the past, but I'm imagining that we can trace back their positions. Yeah, as Roman said, those positions are called co-moving positions in this picture. Okay, so you can say that each galaxy has a fixed position in co-moving space, but co-moving space is being expanded. So I'm just drawing this in what is called physical space, where you see the expansion. You can sense that things are getting, distances are getting further and further away, the galaxies. Okay, so let me draw the last one. So this is more or less what's going on. Yeah. Okay. You can already see that there is an important point here. It's the origin of the space-time, and this is basically what I will call just t equals 0 is the time of the Big Bang. And how do we define it? Well, Roman already introduced the scale factor, so the condition of t equals 0 is just a equals 0. The scale factor is just 0. Yeah? At that point, given that I'm assuming that you took a course on general relativity, you know that we cannot make sense of that point. Yeah, the Einstein's equations break down. It's just impossible to give any analytical sense to what's going on there. Yeah, so basically, this plot is really, it doesn't really start here. It starts some epsilon above this line. Yeah, we cannot make sense of this point. Yeah, so far we haven't learned how to do it. Okay, good. There is another distance apart from the distance of galaxies, which I already draw, which has a lot of meaning in cosmology, and Roman already introduced that distance. This is the Hubble radius. Yeah, the Hubble radius is just the inverse of the Hubble parameter. By the way, I'm working with natural units, so I will take the license to set the speed of light to be 1. Later on, I will set Planck constant to be 1, 2. And I think those will be my two conventions in this lecture. So I hope that's okay with you. So this is important because the speed of light enter into this equation, yeah? And but I'm setting c equal to 1, and therefore this makes sense in that convention. So if we draw the Hubble radius in this plot, do I have colors? Yes. It will look something like, let's choose what's the size of the Hubble radius today. Yeah. So today we live here, so it must be somewhere, let's say here, for example. Okay. So I will just draw a line. This is a straight line from that point back to the Big Bang. Yeah. And you can see, I'm assuming this is a conventional universe dominated by matter or radiation. Yeah, I'm not introducing inflation yet. And in such a universe, this is the picture. Yeah? And at the Big Bang, there are two things going on. The scale factor becomes 0, but also the Hubble radius becomes 0. Yeah? So you could say, well, in this class of universe, we define the Big Bang in that way. Yeah? It is not only the scale factor being 0, it's the Hubble radius also being 0. Yeah? Both things happen at the same time. You can figure it out yourself. Okay? That's what's going on. What's the importance of the Hubble radius? The Hubble radius, among many things, I mean, the Hubble radius appears in every possible manner in cosmology. But there is one particular defining property of the Hubble radius, is that if you had a light signal, let's say you have a light signal approaching to you somewhere, yeah? Which is the color of light, let's say orange. So let's say you have today a light signal arriving to you, okay? So it will do something like that. Yeah, it goes into 45 degrees, yeah, since c is equal to 1, yeah? But remember, this is not a normal plot in Minkowski. This is a universe expanding. So light is moving in a universe which is expanding. Yeah. So as we go back in time, light actually starts to bend in this plot. That's weird, but it is true. This is a special plot in that sense. The plot is showing you how space expands. And so what will happen here is that when it crosses the Hubble radius, in this picture, light is in a vertical direction. Yeah, it's going up. Okay? So this is precisely a vertical line here. And then light starts to bend down, and there you have. That's the trajectory that a light signal follows in this diagram. Yeah? Normally, in a cosmology textbook, you will not find this diagram. You will find another diagram where you draw things in co-moving space. Yeah? Given that that's more typical, I'm just choosing this just for you to compare. Yeah? In co-moving space, you will see light moving in 45 degrees all the way down to the Big Bang. Yeah? Here, it's just bends, and that's the way it is in a space where it is expanding. Please. Yeah, for now, given that this is an overview, this is just a fact. However, I will probably derive it later on. By the way, there are lecture notes that I don't know if they're available right now. They are. So you can take those lecture notes, and in those lecture notes, precisely, there is the derivation of this fact, that a light signal, precisely here, at this point, even though the light signal is traveling towards you, it is actually receding from you. It's not obvious here because you see that, that everything is being compressed into the past. Yeah? But you can see that light is still, if you go to the past, is still traveling towards you in relation to galaxies. Yeah? So you see that all the galaxies are also getting closer and closer to the Big Bang. Yeah? But the light signal continues to travel and approach to you. Yeah? Okay, that's an important thing. So only here, light is basically going towards you. Before, it was sort of getting away from you, in a sense. Yeah. So that's what's going on here. If you were alive here, none of us were there. Light was getting away from you. Yeah. In this diagram, I insist. This is just it's a funny way of looking at things. What is the important thing about this diagram is that you can appreciate something. Is that light in this diagram eventually will reach you. So you will get information about the universe. You just need to wait long enough. Yeah? So if a given galaxy, let's say this one, send you a signal, just because it has stars, you will eventually watch it, and you will see it. Maybe later on this galaxy will be within the horizon. Maybe not. Yeah? But you will see it anyway, eventually. So today, you're actually watching things which are within the horizon, but also outside of the horizon, just because the light signal came out very early on. Okay? A second lesson about this diagram is that even though eventually it will become causally, a region of space will eventually get in causal contact with you, this diagram, and I will like to ask you to spend some time thinking about this, not right now, but maybe later. This diagram is also telling you something, is that regions of space were less and less in causal contact into the past, yeah? Because of this fact. So, I mean, you can think of a light signal that will reach you later on. Well, same rule here, sort of bending, and then they will never match together, only at a = 0 or t = 0. Yeah? But into the past, different regions of sky were worse and worse causally connected. Yeah? Okay? So let's say this region here could never be in causal contact with any other region here. At that time, you have to wait for them to be in causal contact. Yeah? So causal contact only happened into the future in this diagram, not into the past. Things were less and less in causal contact. Okay, that's an important fact about this diagram. Okay? Any question? Great. So basically what Roman will continue teaching you during this week is that, is that you can think of galaxies in a different way. You can really, it's more efficient to think of them, this depends on the scale, of course, on distributions of matter. Well, not only matter, you can also think of distributions of radiation, neutrinos, baryonic matter, dark matter, whatever you think there exists in the universe. Yeah? So it is useful to define the concept of contrasts. So a contrast, and this was already defined, so you already saw this symbol. However, I think Roman did not specify what is he really calling a contrast in a given context, for example, this context. So I will define the contrast, for example, as the variation of the energy density, or just the fluctuation of the energy density over the background of the energy density. Let's put a bar there to mean that. Of some species. So here I could mean, for example, baryonic matter, dark matter, radiation, you name it, whatever you want. Yeah? Even dark energy, if you want. So on and so forth. Okay, so this list could be large. So you define these contrasts, and therefore galaxies, you just replace it by the contrast that describes the distribution of galaxies, right? So now we have here, let's say a contrast of a given wavelength, for example, here. Yeah. So you know that, and we will do this often. We will grab a contrast, which is a function of space and time. And what we will do is to perform a Fourier expansion. By the way, another convention that I will use is that an integral in k, just like that, will mean this symbol. Okay, and an integral in x will mean this symbol over there. Okay, so just shorthand notations for integrals. So bear in mind that the only important thing about this is that this factor is always there when you integrate in k. So it's better to just put it together in a single symbol. Okay, it's just too often that happens. So let's say we expand the contrast into Fourier modes. So you will have here the Fourier mode of contrast like this. Okay, there you have. And what I'm drawing here is a particular Fourier mode, for example, of that belongs to some contrast, dark matter, radiation, whatever you're interested into studying. There is a collection of them, of course, not just one. There's a lot of them adding up, yeah? And I'm just drawing one just for the purpose of following what's going on here. If you go into the past, you can see that because the universe is expanding, then the actual wavelength of this Fourier mode is smaller and smaller into the past. So wavelengths stretch together with expansion of the universe. Is that obvious? I hope it is obvious, right? We will get to the math later, but I just want to remember this is just an overview. So if you follow the wavelengths of this contrast, they are shorter and shorter. Yeah, we're just following the evolution of one mode here. The amplitude might be evolving in time too. I'm just interested here in the wavelength, not the amplitude. The amplitude is we need to study what's going on with amplitude. Here's the wavelength. And if you go into the past, the wavelength is smaller and smaller. Okay, so now the picture is getting a bit uncomfortable. So I will actually make you a zoom here. Okay, where I will get here. So this is a zoom. And let's see what's going on near the Big Bang. Okay, so near the Big Bang, let's draw again here t equals 0. So this is t equals 0. And you have the Hubble radius. Hubble radius is over there. And then this is what's going on. For those things that we know they're there, yeah, for contrast that we can see them, we see these galaxies. Therefore, we see wavelengths in our telescopes, yeah? We can reconstruct them, yeah? So I want to talk about those contrasts that we observe, not other objects. So those wavelengths, the ones that we can see, yeah, as we're close into the Big Bang, we're approaching the Big Bang, they happen to have wavelengths that are much larger than the Hubble radius. Can you see that that's true? That's true because you can see that the Hubble radius evolves into the past at a different rate than the scale factor. Yeah? The scale factor is becoming smaller and smaller, but the Hubble radius is becoming smaller and smaller faster than the scale factor. Yeah? So that means that as we're near the Big Bang, actually the scale factor, which tells you how fast a wavelength is shrinking into the past, is actually larger than the actual Hubble radius. So any wavelength will be always larger than the Hubble radius into the past. If that were not true, then we just need to get closer and closer to the Big Bang. And it will be true that any wavelength that you're interested in will be eventually much larger than the Hubble radius. Now that's critical because remember that the Hubble radius, remember this picture of the signal, gives you information about the causality structure of space-time. Yeah? Remember that regions get in causal contact in the future, not into the past. To the past, it gets worse and worse. And you can see that this is signaling that precisely. Yeah? This is a mode which has a wavelength much larger than this distance, this very special distance, which is telling you something about causality. Yeah? And this is what is called sometimes the horizon problem. It's a version of the horizon problem. The fact that we need to set information near the Big Bang to explain the universe, which defies the concept of causality. Yeah? How do we determine the initial conditions for this contrast so close to the Big Bang? How do we do that? It doesn't matter whether the contrast did not exist at that time. Maybe baryonic matter didn't exist. Maybe dark matter didn't exist at that time. But nevertheless, that wavelength did exist. Yeah? It's a fluctuation of something that later on became dark matter, baryonic matter, it doesn't matter, whatever you want. Yeah? So here we're talking about a fluctuation that exists there at this time, close to the Big Bang. It will continue to exist into the future. It might mutate into something else. It might decay into something else. It might, whatever. We need to understand that, of course. But we know that this fluctuation was there, had to be there. Yeah? So the challenge that we have, and this is what this course will be about during this week, is to understand how this really happened. How is it possible that a fluctuation had the wavelength much larger than the Hubble radius, so close to the Big Bang? Yeah, that's what we want to do this week. Yeah. So let's say, okay, let's fix this time, and let's call this time initial time. It will be the time at where we start the evolution of the universe. Yeah. Because we cannot start from here. I'm sorry. Einstein's equations do not allow us to do that. Yeah? If we try to perturb them and then study what happens at t equals 0, just everything breaks down. Yeah? So we have to start somewhere above t equals 0. There we have. This is that's the timeline. So you have this fluctuation. Yeah? And let me tell you a few facts. And these are actually known from way before the invention of inflation. Yeah? So cosmologists during the 70s knew already that these fluctuations had this feature of having wavelengths much larger than the horizon at that time. When I say horizon, I mean the Hubble radius, by the way. I will use those, even though it's not exactly true, I'm abusing of the language, I cannot avoid it. Whenever I say horizon, I mean the Hubble radius, yeah? For the reasons that I already explained. Yeah? So let me return to the story. During the 70s, even earlier actually, cosmologists already reconstructed this picture. They knew that this was a feature of what is called the Big Bang cosmology, the hot Big Bang scenario of cosmology. Yeah? And they reconstructed with very poor observations, but they were magicians. They managed to reconstruct a few characteristics of these fluctuations here at that time, at initial time. You choose the initial time, it doesn't matter. You can choose it a bit closer to the Big Bang. This feature will continue to hold. Yeah? So at the initial time, these fluctuations, this contrast, happen to share three characteristics. Yeah? This was understood during the 70s. Yeah? These characteristics were, first, adiabaticity. That's the first one. Then Gaussianity. And then scale invariance. Okay, those are the three characteristics that were known to hold true during the 70s. Yeah? Perhaps not exactly. I mean, the observations were very poor at the time. But they managed to assert that fluctuations at that time had to have nearly those characteristics. So if you were going to reconstruct the universe with a simulation, for example, you had to choose initial conditions and they chose those. And then they saw the result of those simulations, and they saw that the universe, with those initial conditions, was fairly matching the universe that they observed, yeah? Even with poor observations at that time. Let me go very quickly through those three characteristics. What do they mean? Yeah? I think I will just delete this part. So adiabaticity remember, this is just an overview, so I'll be plain here. Basically means that the contrast at that time, for example, of radiation, was in phase with the contrast of dark matter, for example. So they were proportional. Well, they were equal, yeah, to be exact. And baryonic matter, and so on and so forth. So you put all the contrast, and adiabaticity means that they're all equal at the initial time. Yeah? Now, I will not justify this, but it is understood that this is there's a good reason why this is true. So I will be sketchy about this. If you, for example, were to examine what's the temperature of the universe at that time, the universe was pretty homogeneous at that time, but there were still different temperatures at different sides of the universe, then you could also talk about the temperature fluctuation, yeah? Delta T, what's the real temperature here and there? So you can actually talk about the contrast of the temperature, if you wish. You can define that. And so adiabaticity basically means this statement, that all the contrasts are equal, even the contrast of the temperature of the universe at the time. Yeah? What does this mean? The actual meaning is very simple. You can imagine that if the universe is well thermalized, you increase the temperature in one part of the universe, and then that also means that the density of particles will be larger in that part of the universe, isn't it? Because the energy density, when you have a local thermalized environment, depends on the temperature. The temperature is a parameter of the state of the universe. So more temperature means more particles, basically, they're interacting. So you will have more baryonic matter, more dark matter, more radiation, more of everything. Yeah? If you have a place where there is lower temperature, you will have less of those things. Yeah? It's basically that. That's what it means, adiabaticity. Okay? Any question? No? Okay. So that's adiabaticity. Let me explain briefly what it means, Gaussianity in this context. Yeah? So Gaussianity. By the way, I haven't finished with adiabaticity. Because this is a good initial condition, then you can actually choose what will be the variable that I want to follow. Because all of them are essentially the same. Yeah? So now that I have this duplicity of variables, I can say, well, I prefer to work with this one. Yeah? Instead of baryonic matter or dark matter, let's work with the temperature. Yeah? And now I follow the dynamics of the temperature. I just study how the temperature fluctuations vary in time in the universe. That's not actually what we do. We choose to work with a different variable. We choose to work with, I don't have space, I will erase temperature. We choose to work with R. This is called the comoving curvature perturbation. Yeah? Let me put the name. So this is the comoving primordial, you could say. Okay, there you have. And R is just one variable that you choose. And the definition that we employ is that it is literally the let's say, the Newtonian potential. I will again cheat you a little bit here in general relativity. So if we draw the metric, if I write the metric, so the metric can be written like this, but we're talking about a perturbed universe, and so I need to introduce a metric fluctuation, yeah? And I will do it in this way. I will perturb the spatial part of the metric in this way, and this is how R enters into the picture, yeah? So this is how it is defined, okay? So this is my definition of the metric. Later on, we will define truly how the metric looks in a perturbed universe. So this defines the curvature perturbation, which you can also choose to study the perturbed universe. And if you analyze adiabaticity, you will discover, you will learn actually this when you study CMB next week, yeah? You will discover that all the contrasts need to be equal to this curvature perturbation R, yeah? So we just call it R, co-moving curvature perturbation. So that's adiabaticity. So now that we have this first condition sorted out, now we can do the following. We can just focus on R. We forget about everything else, just R. So I go back to this picture, and this fluctuation will be just R, okay? Everything else is forced to follow R. Whatever R is doing, other contrasts are forced to do the same thanks to this condition, adiabaticity, yeah? Okay? I hope you learn in better terms why this is true next week when you study the CMB. It's a standard statement when you study the CMB, and I think you have to learn it, okay? So I will borrow this from the future lecture next week, and this is my statement. Only R matters here, and now, from now on, I need to explain why R has this profile. Which profile? Well, of being of respecting adiabaticity, that's sorted out, and now Gaussianity and scale invariance. What does it mean, Gaussianity? Let me go for that now. I think I can erase here. Okay. Let's say we can construct a daemon that goes back to this time and measures the values of R in different parts of the universe. Well, R, so it happens that it's a random variable. Roman explained it very well, that you cannot predict what the value of R is going to be at a given point in space, but you can predict the statistical properties of R. Yeah? So the outcome of what's the typical value of R in a Gaussian universe is given by a Gaussian statistics. Yeah? So let's say you want the value of R at a given point, x. Well, given that we are in a translation invariant universe, the actual point x doesn't matter at all. It just matters its value. Yeah? So let's forget about x. X just is relevant here. Okay? So we're asking about what's the value of R that you will go and measure at a given point. Yeah? This cannot be done, of course, but let's imagine that we could do that. Well, you will find out that the set of values that it acquires in different places in the universe follow a Gaussian statistics. It's that simple. Okay? So if you could work with a probability density function, rho, that predicts you what's the value of R will be, you will find out that this is just a Gaussian. That's the answer, okay? So that's the second property, that's called Gaussianity. Actually, I've been too simplistic about this, yeah? When you do a proper course on statistics, you actually don't work with 1 point. This is called a one-point statistic. It's just focusing on one value of R, yeah? I actually mentioned that R was a function of X, yeah? So let's try to flesh out that. Well, what happens if we do care about R being a function of X? Then you will really work with what is called a functional probability distribution function, which do not care about the single value that R could have, but actually cares about the whole profile of R. Yeah, what's the function of R that you will actually measure? Yeah, what's the probability of measuring one given function R spread out in the universe? That's the question. So this is a bit more sophisticated, and I do not expect you follow exactly what I will say now, but you can a Gaussian statistic for such an object means the following. This is just I will just write some normalization constant n. Typically, is just a divergent constant times the exponential of the following object: 1/2 integraling x, integraling y, and here you have r of x, sorry. Then a special object which is called the covariance matrix. For now, it's just a name times ry. Yeah. So this is a functional. It depends on the profiles of R. If you throw in different profiles of R, this will change its value. Yeah. But this is a Gaussian functional. Yeah. So what do I mean in this context that the curator prediction follows Gaussian statistics? It means this. Yeah. If we're worried about the whole form that R has. Yeah. This covariance matrix is important. It actually is a function. So you can compare both things, and you can understand why it's called covariance. This is called the variance. Yeah. So for that reason, it's called covariance. And so you can actually go for the. I'm lying to you. This is the variance matrix. I will write the covariance matrix here, which is the inverse of the variance. Yeah. So here it is. If you were to write this function, yeah, it's a function of x and y, then you will find the following. I will just write it in Fourier space. I will expand this in Fourier space. And I will now describe what is called, how it is defined, the power spectrum. This defines the power spectrum. Let me just put the symbol R here. Here it is. And you have that combination. Please. Well, because of what at the beginning I say, let's imagine that we measure just the value of R. That's it. Yeah. So that's if you're only interested in the value of R, not worrying about how far it is from another value of R, then that's all you can do. And that's called a one-point statistics. Then you just care about the value of R, and that's the distribution. This is a Gaussian distribution. In this way, we only care about the value of R, nothing else. No. It will change from place to place. Yeah, it's just that given that we have the property that the statistic has to be invariant under spatial translations, then we just go. I go here, I measure the value of R. I go here, I measure the value of R. Go there, measure the value of R. That's it. I do nothing else but that. Yeah. If I do that, then I can draw a histogram of all the values I measure of R. Yeah. And what I will find is that that histogram has this form. It follows this function, and that's called Gaussianity. This is a Gaussian function, by the way. Yeah. But now, of course, you know that R is not a single value. There are different values at different places of space. Yeah. So that's why I'm also offering this more sophisticated tool, yeah, which cares about the shape of R, the profile of R. Yeah. So R really changes from place to place. Yeah. If you only worry about a single value of R at a given point, this is this. Okay, you don't need to do more. But this is more interesting. Because you know that, as Roman explained, you know that you can make two measurements. I can measure R here, and I can ask how correlated they are. Yeah? And that's the two-point correlation function. Yeah? This device here gives you that. The two-point correlation function is essentially this quantity here. Yeah? Okay? And this defines what is called the power spectrum. Yeah? As Roman explained, all of this was explained by Roman. Well, not this part, I guess. Tomorrow, okay. So I will give you an advance of what Roman will say tomorrow. Spatial translation is encoded here. You can see this. This you already discussed with Roman, that this quantity, if it is going to be invariant under spatial translations, then it has to be the difference between the two variables, x and y here. Yeah. Also, we can talk about invariance under rotations. Yeah. Well, all of those things put together introduce this function, which is only a function of scale, k. It doesn't depend on the vector mode. It doesn't depend on k vector. It depends only on k. Yeah. It's a single function of the scale, yeah, of the wave number, not the wave vector. Yeah. So now let me go to the last feature of these fluctuations. This is called scale invariance. Yeah? Scale invariance, I will do it in this corner. Scale invariance. I think I exaggerated, I need more space. Scale invariance means the following. Okay, I'll have to erase it over there. Let me erase this. I hope you got it. Scale invariance is a statement about the power spectrum. So notice that it is not enough to declare that the statistic of the fluctuations is Gaussian. Why it is not enough? It's because you still have a function to define. You still need to decide, if you're writing your code which will simulate the universe, you still need to decide what is the value of the power spectrum. You cannot proceed if you don't do that. You have to choose a profile. So what's the function that we will choose here? What is the simplest function that we can choose? Well, people at that time were super smart, and they declared the following. Let's write things in this way. This is just a redefinition of the power spectrum, which defines what is called the dimensionless power spectrum. Okay? This function delta. Why k to the cube? Can anybody imagine why people at that time were doing this redefinition? Yeah, so the integration is going on, and so there is a volume factor. There is a scaling which is natural according to the volume. It's just the fact that you increase the volume, there is a scaling associated to that. So you want to subtract it. And this is the way to subtract that effect. Yeah? You want to get rid of the volume effect, and that defines what is called the dimensionless power spectrum. And now you have to choose a value for the dimensionless power spectrum where the volume is already factored out. What would you choose now? You were back in the 70s. You are completely ignorant about the universe, about how it started. Well, the simplest choice that you can make is, and here comes scale invariance, is just delta k is equal to a constant. What else can we do? I mean, we know nothing about the universe back in the 70s. So obviously, that's an overstatement, but this is a choice based on ignorance, if you want. There were indications that this was a good choice, of course. You put it back in simulations, and you do obtain things that looks pretty good. Yeah? If you modify this, of course, people did that game at that time, you get different universes. Yeah? So people suspected, yes, this is very close to the right choice. We don't really know what's the correct choice, but a constant dimensionless power spectrum is a fairly good guess. Yeah? Good. That's what happened during the 70s. Yeah? We're approaching the 80s now. Yeah? People were still worried about the fact this was troubling everybody at that time. How do we understand these three characteristics as an initial conditions for wavelengths that are larger than the horizon? The problem of causality is not erased. It's even worse now. It's worse because of scale invariance. You have now a power spectrum which tells you that every wavelength shared the same power. Yeah? So they were all exposed to the same physics. That's impossible in a universe like this. How do we impose here, at t equals 0, that the fluctuations that start here and reach this point, they all have the same power? The amplitude is basically the same in average for each fluctuation. How is that possible? Well, this is inflation. Yeah? Inflation was invented not precisely for that, but in the end became the solution to this problem. Inflation is a change of rules, so this is my definition of inflation. You say, okay, let's be blunt about this. There is no Big Bang whatsoever. Let's erase the Big Bang. Let's go up to the initial time, and let's change the rules of how the universe behaved towards what we thought it was a Big Bang. Yeah? So now the universe extends towards the past. We don't know how far. Maybe to the real Big Bang somewhere there, hidden. It doesn't matter. What we observe starts here. We cannot observe earlier times. So the change of rules consists of the following. Consists of demanding that the Hubble radius becomes a constant into the past. Why would you do that? If the Hubble radius is a constant, that means h is equal to a constant. You know already that h is equal to a dot over a. That's an equation of motion, if you want, for a. And that implies that a is equal to e to the th, or ht. Yeah? That just comes from the requirement that h is a constant. If you do this, the Hubble radius is a constant, of course, that's imposed. But let's ask what's going on with wavelengths now. Yeah? These wavelengths, how were they behaving to the future? They were behaving like this. Yeah? That was the way that, well, here's the wavelength, right? So it was behaving like this. Yeah? There you have, into the future. What happens into the past once you impose that the universe has this change of rules for the Hubble radius? Well, wavelengths evolve exponentially. So into the past, they do this. You see? What an elegant solution, isn't it? That wavelengths that look acausal in this Big Bang universe, they were actually causal into the past. They come from within the horizon. Yeah? That's the solution of inflation. They explain why these wavelengths, these perturbations happen to have these characteristics, because they were indeed subhorizon. Yeah? Here they are superhorizon, and now subhorizon into the past. Yeah? So of course, there's still a lot to do, and we will do this this week. We have to work out what happened here to these fluctuations. But now you have a good idea that whatever happened here, these fluctuations were all subject to the same mechanism, to the physical mechanism, which is causal. Yeah? So we can understand why this acausal profile comes from something which is causal and in that sense physical. Yeah? So that's what I call inflation. This will be the definition of inflation in these lectures. Okay? Of course, you know that inflation was originally devised to solve what are called the classical problems of Big Bang cosmology, such as the flatness problem, the curvature problem, so on and so forth. Yeah? But this will be the important part of this lecture, that we will be concerned about R, about the fluctuation, the curvature perturbation. Great. Any questions? That was my overview. I think it took a bit longer than I expected, but we're now ready to study the evolution of R. Okay? So if you have no questions, I will move on to the next subject, which is quantum field theory. Okay? Good. Let me start over here. Okay, I'm good that you make that question, because I told you that I was going to cheat all the time. So can we really have a pure constant for the Hubble radius? No, of course not. This is just it's a first approximation to this to solve this problem. Yeah. In fact, the Hubble radius, typically in models that we will study, actually still continues to shrink into the past. Yeah. But what happened into the past beyond what we called inflation, we don't really know. Yeah. So how did that start? Did this start from a Big Bang too, from a previous Big Bang? Honestly, we don't have a criteria to say that. So there are models which are called, for example, eternal inflation, which suggests that yes, that the Hubble radius did get to a point where you could call it constant, and now different universes emerge from there, and they have different Big Bangs and so on and so forth. This will be an educated version of the multiverse, if you want, in that sense. But this was, joke beside, this was a real concern during the 80s when people started to figure this out. So eternal inflation was realized that, oh, this is a scenario that will emerge, we like it or not, from certain type of models. Yeah? Good. Any more questions? Okay, so let me give you a brief version of quantum field theory, which is useful for what we want to do in the following sessions. Well, we must do quantum field theory, and that normally means that we need to work with what is called the Heisenberg picture. Yeah? So typically, the way you start studying quantum mechanics is by writing, for example, the Schrödinger equation, which is, I will write it in this notation. There you have. Okay, that's the Schrödinger equation. It's a good idea when you work with fields, I will introduce fields in a moment, to move on to the Heisenberg picture, where basically the evolution of the mode, of the state, sorry, yeah, is mapped by what is called the unitary evolution operator. Yeah? So this could be written like this, for example, acting on the state of the system at some given time. Let me call it just psi naught to refer to what we know about the state of the system at a given time. Yeah? This operator is unitary. That means that the information here of the system is the same information that you will find later on. Yeah? So it's up to you. If you want to work with a state which is time-dependent, that's good. But you don't gain anything, really, because it's the same information here or there. Yeah? So having that view, you can actually just declare that the state of the system is this time-independent quantity, yeah, this vector, and move the time dependence to other objects, for example, observables. Yeah? So you could have an observable, and now you say, well, the observable will be time-dependent. It is useful to be time-dependent by writing the time-independent observable, whatever operator you define to be your observable, which is time-independent, well, you promote it to be time-dependent that way. Okay? This is it's a good attitude in my opinion, yeah? Because now you can work with equations of motions, for example, for these time-dependent operators, which are going to be found to be given by this form, right? You probably saw that in many occasions in some context. Yeah? This just comes from the definition, from this definition, and from the fact that thanks to this function, the unitary operator, by the way, I should have told you this first. The unitary operator satisfies the following equation, satisfies that. So where does this come from? It comes from the Schrödinger equation, our starting point, yeah? And now that we define these time-dependent observables, you can actually work with this equation here, yeah? It is just that. Sorry, I mixed the, oh no, it's fine, it's fine. It's fine, the signs are okay. In my notes, you will see that this is inverted, so let me just do it immediately, otherwise I might I might start writing things that look unfamiliar. Okay. Good. Now you see the role of the Hamiltonian. Yeah. You all know that H is called the Hamiltonian here. The Hamiltonian evolves the system, yeah, from a given time to the next time. I will dare to say that it's the most important object in quantum mechanics. Yeah? If you don't know the form of the Hamiltonian, you can't do anything to study a system. You have a system ahead of you. The first question you should ask is, what is going to be the Hamiltonian I choose to study the system? Yeah? How do I choose the Hamiltonian? Imagine that you were confronted to a dilemma of the beginning of last century, after the creation of quantum mechanics. Should I say creation, invention, or whatever, or discovery, as you wish. And after the discovery of special relativity. Yeah? You know the story that people started asking, well, what is the Hamiltonian we have to choose to describe a relativistic system, a system that shares Lorentz invariance as a fundamental symmetry? Yeah? There were many guesses. There's a whole beautiful story written there. Dirac had a role there. Yeah? I will give you sort of the perspective more close to what you will find, for example, in Weinberg's text, which I think I like a lot. Yeah? So Weinberg suggests that the way that you can ensure that the Hamiltonian is going to be relativistic is by constructing the Hamiltonian with fundamental quantities which are representations of the Lorentz group. Yeah? And these are called fields. Yeah? So let's introduce the concept of field. It's an operator, so let me call it field operator, which depends on space and time. There it is. Let me just collect space and time into a single variable, x. There it is for now. Later on, I will return to space and time. And so this is a fundamental quantity which has a purpose. The purpose is to allow you to construct Hamiltonians. That's the only purpose they have. Nothing else. And they have to be representations of the Lorentz group. What does that mean? That if you consider Lorentz transformation, for example, that one, so you're working with x, but now you move to a different frame, or now you start working with x prime. So that's the transformation. Lambda is a Lorentz transformation. Then, for example, this field, which I will call a scalar field, has to transform according to a special rule. This rule happens to be the following, that by doing this transformation, you get a new field, which I will call phi prime, but it will be evaluated at x prime, the new coordinate system that we're working with now. Yeah? So there are two things going on. The coordinate system changed, but also the field changed. Whenever you see this, you can say, this is a scalar field. This is the way a scalar field transforms. Yeah? That's the way we define it. You can actually work with this and derive from here a very simple rule that phi prime, if you want to know the form of phi prime as a function of x, yeah? Not x prime, but x, you can see that this leads to the following rule. You can derive it from the previous rule, do it yourself, okay? It's not so difficult, okay? So this is what we call a scalar field. Other fields transform differently. For example, a vector field transforms in a different way, a tensor field transforms in a different way, but I will focus on scalar fields, okay? Good. Now, this field exists everywhere in space and time. How do we find the form of this field operator? How can it exist in every possible form, or is subject to constraints? Yeah? Well, I will declare that because this is a field which represents, is a representative of the Lorentz group, it cannot change from place to place in an arbitrary way. It has to follow some equation. And this equation has to be Lorentz invariant. Yeah? Otherwise, it's not a good device to construct relativistic theories. Yeah? So for example, we could force, and this is for enforcement, there's nothing fundamental here. I will force that the field satisfies the following equation of motion. This is fantastic because I'm forcing an operator to satisfy this equation of motion. Yeah? By the way, here, this is the Lambertian. This is just shorthand notation for this combination, right? Okay, so why are we writing this? It's because we want the field to behave, we want the system to be relativistic in the end. Yeah? So we are guessing that this is a good way to keep it relativistic, that this basic brick to construct Hamiltonians must satisfy something which looks Lorentz invariant. Yeah? Okay, so if we do that, this is an equation of motion, and don't confuse it. This is not a classical equation of motion. Be careful. This is an operator satisfying a certain type of rule about how it can change from place to place. Yeah? It's not the same as a classical equation of motion, which will come later. Yeah? But of course, you're all staring at it, and you're saying, well, what the hell? It is an equation of motion. Yeah? Not only that, you know that this equation of motion comes from a least action principle, isn't it? Yeah? So there is some action somewhere, we can design it, that by varying it, it gives you that equation of motion. Yeah? Of course, this action is not written for an operator, it's written for a number, for a C number, not a Q number. Yes, let's extend it to Poincaré. No problem. Yes, yes, yes. I'm just focusing on the Lorentz side of it, but spatial translations are part of the game, rotations too, that's fine, yes. So nothing of this is too specific to Lorentz, yeah. Thanks for the question, yeah. Yeah, so can you help me to write this action? Well, let's do it in the opposite direction. Okay, I guess it will be something like this, and then the form of this, the action that I should write is given by d phi squared half plus minus, sorry, v of phi. All of this is more details in the lecture notes, by the way. But okay, do you agree with me that this gives you that equation of motion by varying it? Yeah. If you're not familiar to classical field theory, this is not too different from just conventional one-particle classical mechanics where you play with an action, you can vary it. And, so this action indeed gives you that. Yeah. Okay. Now I'm a bit worried about the following. Yeah? We're doing quantum mechanics. This is an operator. In principle, it's an observable. Or I wish that it is going to be an observable, that it has consequences for the real world. So does it actually satisfy this equation at the same time? You see, we have two equations now, two equations of motions. We have that one over there, which is trying to enforce Lorentz invariance, or the Poincaré group. And this one, which is quantum mechanics, basically. It comes from the Schrödinger equation. Let me write it one with the other. So here we have the Lorentz invariant equation, but also at the same time, we have, I will write it in a version that we have the field now. We have this, we have these two equations. So look at it, look at them together, and you might be worried that you can actually impose them at the same time. Yeah? Maybe they're not compatible, really, that quantum mechanics doesn't allow you to get to this constraint on the field operator. Maybe it's fine for the classical field, but not the actual operator. Can we actually ensure that both things are compatible? If we manage to do that, then we achieve a relativistic theory. Yeah? So the question is whether there exists a Hamiltonian that does this. So to answer this question, I will guide myself with this action. By the way, I consider this to be important because we will be writing actions all the time when we do cosmology. I mean, many of you will go into pyramidal cosmology and you will want to model inflation in some way, and your starting point will be to write an action for your theory with fields, one field, two fields, multi-field inflation, whatever. So this is normally a starting point, but we should be sure from the start that whenever we quantize this field, we're not doing something which is incompatible in a sense. Like quantum mechanics do stay compatible with this other equation, which is an equation of motion. So how can we know this? Well, let's have a look at the classical theory, yeah, which is here. That's a quantum theory. Here we have a classical theory. And I think I would say a few things that you already know about the classical theories. One of them is that if you start from here, you can define what is called the momentum, yeah? And the momentum is just the derivative of this against, it's a functional derivative of this against the speed of the field. So basically, you will find that momentum is just phi dot, yeah? They depend on x and t, yeah? And then, by knowing the momentum, you can extract the Hamiltonian. There is a set of rules for that. I will not go through them, yeah? So you can write the classical Hamiltonian, not the quantum Hamiltonian, yeah? And the classical Hamiltonian, you will find it to be basically, open up here. I hope this is familiar to you. You will find that. That's the classical Hamiltonian, written in terms of the field that you have. Notice that this actually depends on time. We only have integrated x here. So you have time as a variable that appears. Yeah. Now, what did you learn in your course of classical mechanics? Is that these objects satisfy certain rules, which are called equations of motions, classical equations of motions. These are the Hamilton equations. Yeah, I will go over here. How much time I will, how much? 15, okay. Good, so what are those equations, the Hamilton equations satisfied by these, by that Hamiltonian? These are the following. Well, those are called Poisson brackets. I will not write them down. What's the definition of the Poisson bracket? Yeah, they're in the lecture notes. I think you know what are Poisson brackets. However, what is more important than that there is a definition for the Poisson bracket, which there is, of course, is that they share some properties. Yeah? And the properties are the following. First of all, you can verify this one, which is obviously very well known. It's antisymmetry against interchange of the quantities that are evaluated at the Poisson bracket. And then you have a series of other properties that I'm not writing down just because I'm assuming that you know them all. These are algebraic properties of the Poisson brackets. One of them is linearity, another one is called the Jacobi identity, whatever. These are algebraic properties. So there is a definition for the Poisson brackets, but the real important thing about those definitions is that the Poisson brackets satisfy these rules. Yeah? These 4 rules that are somewhere there in the lecture notes. These are equation. No, I don't have the equation, sorry. Okay. Now, here comes the important part. These 2 equations, together with these properties, they imply the following equation. They imply this equation. And you can see that that equation is very similar to this one, for one minor difference, well, a huge difference. This has a field operator. That one has a classical field, yeah? The inflaton, if you want, whatever. We're going to study inflation soon. The important thing here, I want to stress, is that this, how to get from here to here, is just pure algebra, yeah? You just enforce these rules here, yeah? So if you're paying attention, you might see that we accomplished this part, but we want to make this consistent with this. And now I hope you see that it is possible, indeed. It is possible because there is here an object which is called the commutator, right? You know the commutator of quantum mechanics. And the commutator precisely satisfies those algebraic rules. Yeah? They share the same rules. So this thing is equivalent to these two. Yeah? Sorry? Partial. I'm losing you. Where? Oh, yes, yes. That was a big difference. Yes, thank you. Thank you. I just put a little phi to mean a derivative against phi, by the way. So you can see this is really important. Now, this equation here is not incompatible enough anymore with this one. Why? Because if we promote in this picture this rule, these algebraic rules, which holds for the commutator, if we just force them for the commutator, yeah, if we just, well, we're not forcing them. You know that the commutator satisfies those things, then these two things are equivalent indeed, yeah? They're equivalent, and how? You just need another field. Where it is? You just need a second field. We'll write it here. So you see, to make these two things compatible, you just need one extra ingredient. This is what is called the momentum operator. Yeah? It's a partner of phi. Phi is never alone, has to be together with somebody else. It's an observable too, yeah? And it must satisfy the following rule. And you see that if these two things are now equivalent to this, yeah, thanks to the algebra that we just discussed, together, I cannot forget to mention this is the most important part perhaps, together with another condition. Let me go to this side, to the classical side. You know that phi with pi, what happened with them in the classical field? If we do a Poisson bracket between phi and pi, do you know what happens? They become proportional to a delta, a Dirac delta. I didn't tell you that here we have x, here we have y. Yeah? What happens if you have phi with phi? Now it's true, now it's 0. And what happens if you have pi with pi? You have 0. Yeah? So all this story works if we now also declare that phi, operator phi, x, time with pi, y time, the commutator of this is equal to I delta, x minus y, and finally, well, the rest is just 0 and 0, yeah, phi and phi, pi and pi, okay? And so this is the quantum commutator between the two fields, the inflaton, for example, and its partner, its momentum, okay? It's canonical momentum. Okay, to finish this today's lecture. So let me just digress a bit again. That this is quite fundamental to understand because we need to write models of inflation, and we need to study the quantum behavior of these models. So it is important to be sure that when we write a Lagrangian, we're indeed producing these quantum relations. Yeah? And these quantum relations ensure that the Hamiltonian actually evolves the system in a relativistic way. So if the Hamiltonian is written in terms of phi in the way that I just deleted, but it was here at some point, yeah, then that Hamiltonian is a relativistic Hamiltonian. That's ensured. There's no way out. That's it. That's the rule of the games. This is how we can be sure that the quantum field theory indeed produces a correct relativistic theory. Now we can just play and see the details now of how this works. Yeah? So I will end up today's lecture doing the very basic exercise. I will sketch it because I think many of you already know this in detail. So now I start with an action, yeah? Or Lagrangian, doesn't matter. So now comes the artistic part of the game, yeah? Let's describe the universe. Let's start by writing an action, yeah? So that's how we do in primordial cosmology. And I will, for example, take the following action. There you have. That's a Lorentz invariant action, or Poincare invariant if you want. And let's see what happens with the quantization of this field. Yeah? Of course, the associated equation of motion for the operator that you know goes hand by hand with this, yeah, is the following. Is that one, yeah? So you know, this is not a classical field. That's a classical field. But this is a device to be sure that your quantum field will follow an equation which is Lorentz invariant, yeah? So they go hand by hand. They're related somehow. But this is a device. This is the true thing, yeah? Of course, they're related in ways which are worth studying. We will not do that. And to quantize this, I will do the following. I will propose the following ansatz. I will propose that phi can be expanded in Fourier modes. Yeah? So the expansion I will propose here is the following. I will introduce what are called mode functions. These are functions, not operators, that mimic the evolution of the field. Okay, so those are called mode functions. I will introduce a set of operators. Here's where the operator nature of the field comes about. So this will be B daga. Sorry, B tilde. And then B hat, sorry, the symbol was escaping to me. We write that. That's just the Fourier mode instruction. Then plus the conjugate, and now I need to write the daga of the field of the operator. Sorry, e to the minus. Well, you know what to fill here. I don't have space. There you have. That's the proposal. Yeah. So we want to quantize this. I mean, that's already quantized. Yeah. There you have the field. Now we need to understand what are the details of this. So an exercise that you will be dealing with consists the following. You already know how to define the momentum operator. This is just phi dot of x t. That comes from the rules that we already examined. And now you have to impose the quantum commutator. That means phi of x. This is the equal time commutator. You have to impose that. So you pick up this quantity, you pick up this one too, you put them together, and you study how does this object look at the left-hand side, and you have to match it with the right-hand side. Yeah? That's a good exercise. And you should find, as an outcome, that these operators B cannot satisfy everything, cannot be anything. Well, there are two first things. Sorry. Let me order myself, and I'll finish here. You plug this here. What do you think will happen? It will give you an equation of motion for the mode functions. The mode functions you will find satisfy this equation of motion. Yeah? You know how to solve that equation of motion, right? That equation of motion has a solution, which I will write in this way. We'll write it as alpha k e to the, let me see the order of things, minus omega t plus, no, I will use here minus. There you have, that's the most general solution of that equation of motion with two integration constants. Yeah? So next step of this problem. Grab these two things, put them here, knowing that this is the solution, and you will find the following statements to be true. You will find that, first, this condition. Okay, that's the first condition. Whenever you see these, you can call them, you're free to call them in this context, Bogoliubov coefficients. We will study their importance in a moment. Well, tomorrow. And the next thing you will find is that these operators are not anything, but they have to satisfy the following algebra. The commutator between B and B daga is equal to 2 pi cube that, and then any other commutator that you can compute between B and B daga are just 0. That's what you will find. Okay? I think I can finish here. This is an important outcome, and what we need to do now, we will do it tomorrow, is to explore this condition here. This will be important for inflation. Yeah? And we will compute what is called the spectrum of the theory. You have done it so far in the past. And then we will move on to study the quantization of the field in time-dependent backgrounds. Yeah? And we will see that many of these steps are actually, they are just the same. There are no statement I have made here that will not be valid for time-dependent background. Okay? So I think I can finish here. We're on time. Thank you very much for today. Yeah.
No, just a comment. Thank you very much for your letter. Well, it's okay? Okay. Well, in your letter, you are assuming that the universe had a beginning, right? And in this, if the universe had a beginning, indeed, inflation is very, very important. But perhaps when you approach the singularity, perhaps new physics appear, and then perhaps the universe did not have a beginning, perhaps stay forever. And then in this situation, maybe inflation is not necessary, and also in this, and there are many models nowadays, the bouncing models, cyclic models, Penrose-like models, in which you can obtain these three things that we have there. So I just wanted to
let me offer a back comment.
Okay.
I mean, the Big Bang, the hot Big Bang scenario, you could say it's an easy thing to infer from observations. I mean, you see the universe. So I'm really dealing with that scenario. Yeah, that scenario assumes a big, well, it has a Big Bang in it. I don't know if it assumes it, but it has it. Yeah. That scenario assumes certain type of matter fields, conventional matter fields, radiation. So with all of those ingredients that you observe, that universe do have a Big Bang, right? if you don't assume something else. So to tell you the truth, in my personal taste, the universe could be eternal if you want, or it could have a phase, very weird phase prior to inflation, or even there could be no inflation whatsoever. So I totally agree with those statements. But my attitude here is just that inflation solves or deals with a very specific characteristic, which is to explain why curator perturbations, or why the perturbations are adiabatic, Gaussian, and scale invariant. Yeah? So for me, that's the importance of inflation. If there is a competing theory that achieves that, I will move to that theory. Yeah?
I'm not saying to move, but just there is this alternatives.
Yes.
And also, the beginning is not inferred by observation, because you don't know what happens really near the singularity, because you don't have any theory, right? Okay, just
absolutely.
Just.
I totally agree.
More questions? Yes, I guess people are hungry. Okay, so let's thank Gonzalo again for the lecture. So you probably received information how to have lunch around here, right? Hopefully. So yeah.